Good day, this is Jim Pytel from Columbia Gorge Community College. This is Digital Electronics. This lecture is entitled Digital to Analog Conversion Methods, Binary Weighted Input. We're going to continue our lecture series about digital signal processing, and up to this point we've been using the same diagram. We've kind of been right here. Okay, we've talked about our input filtration, the sampling and holding, the conversion of analog to digital using the analog to digital converters. Now we're going to go ahead and take it home and basically do the latter half of this, namely DSP itself. In some general terms, we're going to talk about specific methods of digital to analog conversion and our output filtration. One of the things what I'd like to kind of clarify is right here, is this realm in the middle here. Everything to the left of that block is analog. Everything to the right of that is also analog. The DSP does not convert analog to digital, nor does it convert digital to analog. Those are jobs for the analog digital converter and the digital to analog converter, respectively. Sometimes a DSP is referred to as an ADC, a DSP, and a DAC together. For our purposes, though, we're clearly differentiating those three functions. What does an ADC do? It converts analog to digital. What does a DAC do? Digital to analog converter. Obviously, it converts digital information back to analog. What does a DSP do? Well, look, it does a lot of things. So basically, a DSP, it's a special type of microprocessor. Like we had our very brief introduction to microprocessors. What is it? It's got a CPU and memory, and it's optimized for speed. What is a DSP doing? It's processing digital data. Notice where I've got that block there. That's all digital data. What does it do with that digital data? You know, some of the basic functions of digital, what we've already been talking about. Perhaps it could be multiplexing that digital data, demultiplexing it, perhaps compressing it or decompressing it, filtering, taking unwanted signals out, or perhaps separating signals, from a certain frequency, adding and subtracting digital information. In the case of perhaps the recording industry, that's music, analog music, you're adding some other digital sound to it. One of the easiest ways for us to describe the function of this DSP is to use the same linear diagram that we've had and kind of just make a little horseshoe out of it. This is the easiest way for us to describe, because this linear diagram here seems like we're painting the house and then unpainting the house, which sounds kind of stupid. What I've drawn here in the secondary diagram here is kind of a very quick block diagram of a cell phone DSP. And the DSP is, think of the red. The red arrows are outgoing information. The blue arrows are incoming information. And the cell phone is talking to another cell phone. Say, for example, the red arrows here. You have analog speech coming into your microphone, and it's got your input filtration, your sample and hold. It's now being converted, that analog signal. Perhaps there's an amplifier in there. Maybe it's a weak signal to begin with. Now it's going into that analog to digital converter, converting it to digital information, and then it's being sent to the DSP. At this point, you could perhaps be compressing that digital data. I'm not going to go into the specifics of coding or compression, but what is compression? Compression is the reduction of a number of bits, reduction of a giant data packet to a smaller number of data packets. One way this could potentially happen is if there's a lot of zeros. If you expect a lot of zeros, compress that long string of zeros into a shorter string. Same thing for ones, but realize compression, it's the reduction of information, potentially with a loss. Potentially that's, for example, an MP3 code for music. You've lost some information versus some of the other higher fidelity formats, okay? So compression is the reduction of information, reduction of that audio information. The DSP, once it's got that digital information, what's it doing with it? Now, this is the point. It is digital information. You could potentially error detect, error correct. You could perhaps encrypt this transmission, and at which point it's basically got that digital information. It's going to hand it off to the RF transmission portion. In addition to all that, doing something with the data, the DSP is also handling the protocol of cellular communication. For example, you are driving in your car, as opposed to paying attention driving, you're talking on the cell phone, but you're traveling from cell to cell. It's handling that handoff between different cells. Okay, the DSP, in addition to handling that digital information, it's also handling the communication protocol. The RF transmission now at this point sends that out into space. Okay, and you're going to have to take another course to figure out how RF transmission works. Now, information's coming back in. The RF transmission is accepting digital data that's perhaps been compressed or encrypted and with potentially with some errors in it. What's happening to the DSP? Well, it's correcting those errors. It's decrypting it and decompressing it and being sent to the digital to analog converter. At this point here, that's when it's analog information. It is going to, based, and we'll talk about this in a little bit here, it's going to have that stair step function that we've used to in digital world. We don't necessarily want those high frequency components, so what we're going to try to do is smooth that out using our output filter, sometimes known as a reconstruction filter. Potentially we need an amplifier to amplify that, and at which point analog information comes out of that speaker. So having this little horseshoe bend, which I'm talking about, is right here in our previously linear diagrams, may help you understand how this whole thing works together. The DSP itself, it's not just going ahead and convert it analog into digital, then back to analog in this direction. Why would you ever do something like that? There's an interface between that DSP and perhaps another system. One quick note here too about the actual construction of the DSPs. They are very similar to a microprocessor. Like I said, there is a memory and a CPU. Most DSPs have what's known as basically a two-memory, a binary structure. There's a program memory and a data memory, okay? Because it's handling these things in real time super fast. You want to have data memory separate from the program memory. In addition to that, think about what we discussed in microprocessors. There's an address bus and a data bus. For example, like think about here, I'll just draw a diagram here. Here's your CPU for your DSP. There's an address bus and a data bus for the program memory and the data memory. So there's your data memory. It also has an address bus and a data bus. Same thing with program. Address bus, data bus. It's a little bit more complicated because you're trying to accomplish these things at such a high rate of speed. One brief note before we go on to specifics of a digital to analog converter is there are other methods of analog to digital conversion. And in the cell phone example I used here, they don't typically use some of the previous methods I talked about to analog to digital conversion. Most normally they use with this thing known as a delta modulation. Sometimes it's called a sigma delta analog to digital conversion. It's kind of like successive approximation, but totally more complicated. The easiest way to describe it, I guess, you got a string of bits. I think you've got a positive maximum, a zero, and a negative maximum for your analog signal you're trying to represent. And let's say you've got a 3-bit system. 3 zeros represents the negative maximum. 3 ones represent positive maximum. What's the middle? Obviously the middle of that range. What sigma delta or a delta modulation means is basically it's a use of a little bit of a feedback with a digital to analog converter. So it's constantly comparing that. If it's higher than what the previous sample was, it's basically, okay, add another one. If it's higher, add another one, add another one. So this stream of ones and zeros comes in where the number of ones represent how close it is to the positive maximum. A number of zeros represents how close it is to the negative maximum. Don't worry about the specifics of that, but that is typically the method used for a cell phone. So here, let's talk about some general terms about digital to analog conversion before we go into some of the specific methods. Obviously, what does a digital to analog converter do? Basically, it converts your digital signals back to analog form. And think about the number of bits. 3 bits versus, that's 8 steps versus 4 bits. That's 16 steps in there. That's resolution. The term I've been using is granularity to think about a beach. Where are you most likely to have a beach party? Something with sand or something with sharp-edged boulders. Okay, those sharp-edged boulders have significantly less granularity. There's less of them on that beach. So what is resolution or granularity? It's a reflection of the number of discrete steps. Accuracy, this concept of accuracy, is if you expect a certain value, you have to compare it with what you get. There's a certain realistic expectation you could have. It typically expresses a percentage. What you're doing is you're comparing your expected versus your actual obtained. Okay, this concept of linearity, think about this. We can go from 0 to 15, i.e. 16 different discrete steps there. The linearity, basically, if 0 represents 0 volts and 15 represents, just keep it simple, 15 volts. we should see a linear relationship. When I say 7, i.e. binary 7, I should see 7 volts coming out. Okay, so that's linear. Any deviation from that typical linear structure, think about this term of monotonicity. As I progress from quadruple zero up to quadruple 1, I'm constantly increasing in nature, whereas non-monotonicity is basically I'm going up and for some reason I step back. Basically, that's what a non-monotonic error is in perhaps a digital to analog converter. And this could represent perhaps some particular bit position that is constantly stuck at 0 or constantly stuck at 1, or basically some error within our digital to analog converter. As I said earlier, you expect there to be an equal range. Think about perhaps there's a high gain at the high end or low gain at the high end. Be aware some of those errors that can occur there. We want that linear approach. In addition to those gains, there's also called the differential nonlinearity. Perhaps we're doing fine here, and then all of a sudden we start tapering off inaccuracies at the higher end of that range. Very similar to some of the nonlinearities there. It's still linear, but could you imagine perhaps an offset? I'm trying to draw that parallel where 0, 0 accidentally is being represented as 6 volts, or perhaps a negative offset. Those are undesirable characteristics. Finally, settling time. It takes time for this thing to come through, and be aware if you're handling speech at high rates of speed, perhaps over long distances, there might be a delay that's involved. Most of the times it's not noticeable, but be aware that you want these things to occur, and if you're happening at an incredibly fast rate, these things do not occur instantaneously. Be aware that there might be some time for it to go ahead and go through the the decompression, the unencryption, the error correction, then the actual conversion of that digital information back into analog, going into your filtration, your reconstruction filter, and your amplifier. It's going to take time. Okay, so be aware of these things in your specifications. Last but not least, let's just talk about this concept of the output filter. Sometimes it's known as a reconstruction filter. Like I said previously, we are used to our digital stair step. As we convert this digital information back into analog, like I said previously, everything is composed of sine waves. Those rapid changes, what I'm talking about, those rapid stair steps are inducing these high frequency components into it that could potentially be filtered out with perhaps a low pass filter. If you're going to go ahead and reconstruct here's the actual output of your digital to analog converter. So this is our actual output. That is what is the digital code is outputting that stair stepped. What we're going to do is put it into our reconstruction filter, and it's going to give us that smoothly varying analog signal, very similar to perhaps what was coming in our desired effects. Okay, notice the difference between the green and the black there. There's none of that stair step in there. It's giving that nice, desirable analog signal. So let's actually go into our first of our specific digital to analog conversion method, known as the binary weighted input method. Before you begin this, please make sure that you understand the basic operations, the operational amplifier. So if you need a refresher of the operational amplifier, go back to our first analog to digital conversion method, and I give you a very brief description of how an operational amplifier works, and I do not need you to go to any more specifics than that particular lecture there. I know you perhaps already know how these things work internally. All I'm asking you to do is understand at least that level of difficulty before we go into this first of our digital to analog conversion method. So the first digital to analog conversion method we're going to discuss is the binary weighted input method. This method uses a resistive network where each bit position has a weighted input to a single current summing junction. The smaller bit positions have less influence, i.e. less current, and the greater bit positions have more influence, i.e. more current. So how would you do this if digitally we're representing binary values with the same voltage input, i.e. 5 to 0 volts or 3.3 to 0 volts if you're using CMOS? Basically, how you're going to use this is inversely proportional resistors. Okay, so notice my highest order, the MSB in this particular network, the 2 to the 3 versus my LSB. Okay, so what I'm doing is these combination of resistors where my MSB gets R. The next one down gets twice the value of R. The next one down gets 4 times the value of R. Finally, my LSB, in this particular case, it's a 4-bit system. It is getting 8 R, where the number of bits, basically my lowest order magnitude, gets the 2 to the n minus 1 R. Okay, so if it was a 5-bit system, I would start off with R, and then I would go down to potentially a 16 R for that 2 to the 0 position. And how this works, again, is like I said, is it's a current summing junction where the MSB can contribute a certain amount of current, and so can each one of these. And look what's happening there. All of those currents have one path, namely through RF, because according to our properties of operational amplifiers, no current enters that operational amplifier. And additionally, why is current flowing in the first place? Well, because that inverting input is being held at the same potential, i.e. a virtual ground, so 0 volts right there at the inverting input. So actually, let's just put some real numbers onto this network here. Here is a network where, let's say we're using TTL compatible logic, 5 volts down to 0 volts, and we can apply our MSB down to our LSB here, a specific number. And what each one of these bit positions contribute to this? Think about the current through the D3 resistor. Notice we're starting at 10K. The next bit position should have 20, the next one should have 40, the next one should have 80. I've set up our operational amplifier so it actually amplifies our signal. You'll see this in a little bit here. If just the D3 position is activated, i.e. I put 10000 on this network, okay, I've got 5 volts across the resistor hooked to D3 because look, I've got 0 volts here. Okay, think about what is the current through that 10 kilo ohm resistor when there's 5 volts across it. Perhaps you've heard of Ohm's law, where current is voltage divided by resistance. So it's 5 volts divided by 10K. I should get 0.5 milliamperes. It's a very small amount of current, and they will get smaller as we go through. Because again, what is a transistor? Well, it's a transistor-based operational amplifier. Basically, those small currents control larger currents. So with 0.5 milliamperes coming into that junction, where does it go? It has to go through there. What's the voltage drop across that 20 kilo ohm resistor when 0.5 milliamperes going through it? Well, perhaps you've heard of Ohm's law, where voltage is current times resistance, but because we've got 0 volts at one end, how does conventional current, still travel at that end by V0 becoming lower? So we're going to get a negative value. What you should find is the voltage drop across that 20 kilo ohm resistor. Our V out should have negative 10 volts. Okay, we've amplified it. Okay, so it's pretty cool. So what is, when I put in the digital code 1000, I get out an analog voltage right here of negative 10 volts. So go ahead and figure out what is the contribution for each, the current contribution for each one of these resistors. So for example, 0, 1, 0, 0. What is the current through the resistor hooked up to D2? What is the current through the 20 kilo ohm resistor? What is the output voltage when that is applied? Do the same thing for this combination and do the same thing for this combination. You'll find the following values. For the respective bit positions I've set up here, there is the contributing amount of current. Here's our output voltage induced by that current going through there. And you realize the current summing junction. What I'm saying now is if D3 and D2 and D1 and D0 are all ones, think about all those currents coming together respectively: 0.5 milliamperes, 0.25 milliamperes, 0.125 milliamperes, 0.0625 milliamperes. What's that add up to? 0.9375 milliamperes. When 0.9375 milliamperes is going through a 20 kilo ohm resistor, what is my output voltage? It should be negative 18.75 volts. That is representing the output when I have all 4 ones. What's my output when I have all 4 zeros? Well, the answer is obviously 4 zeros, 0 volts out. So you see what's happening here is basically I can represent digital data, quadruple 0 up to quadruple 1 in this range from 0 volts down to negative 18.75 volts. But what's my resolution? Okay, the answer is right here in 1.25 volt steps. So I can represent 0001 as negative 1.25, 0010 as 2.5, 0011 as negative 3.75. You see what's going on there? I'm establishing that linear range from quadruple 0 all the way to quadruple 1. They should linearly behave, okay? Those concepts of non-monotonicity or some high gain or low gain or offset, we would see perhaps an error in that representation. So I'm going to go ahead and draw a quick graph of what this thing should look like ideally. So this is a tabular and a graphical method here illustrating the resolution and range of this particular setup of a binary weighted input digital to analog converter. So notice here what we've got is quadruple 0 to quadruple 1 representing 0 volts down to negative 18.75 volts in our 1-bit steps, where each step represents 1.25 volts. And if we were to go ahead over the course of time, put in the combination, perhaps with some counter, generate quadruple 0 to quadruple 1 and a time varying waveform, what we should see is this nice, again, linear ramp. Every time we go 1 bit higher, we go to the next resolution step. If there were some problems perhaps with an offset, we could potentially see, let's say, 0 really, you're trying to represent quadruple 0, you should see 0, but you're in fact seeing -5. There might be some problem there. Let's illustrate some non-monotonicity. Perhaps one of the bit positions is stuck in 0. Let's go ahead and see if you could figure out which bit position is causing it when I give you this graph here. So what I've done is here I've introduced an error in the conversion of this digital signal to our analog output here, and what I've got here is our expected value is that nice linear slope, that black value. However, what we're observing is this green stair-step waveform here for those individual combinations. Okay, so look at it and see if you could figure out which bit position is the problem. And notice, okay, at moment here, it is combination 0001, this being the MSB, that being the LSB. As we'd expect, we're getting negative 1.25 out. But as we step up to the next one, we would expect negative 2.5 for the combination 0010. However, we're getting 0 volts out as indicated right here. So I might suspect D1. Okay, let's go on and see what happens here. So when we move to 0011, I should expect negative 3.75 volts, but what I'm getting is negative 1.25 volts. And as you progress through, you'll see this repetitive pattern. It goes up, back down. So that's non-monotonic. It's as we'd expect. It should go as we continue to progress from 0, 0, 0, 0 all the way up to quadruple 1. We should see that nice constantly increasing, but we're stepping back in time. And yes, the answer is D1 is constantly being held in a 0 position. You're comparing your actual results with your expected results, and you're going ahead and figuring out, okay, what is the error that I'm observing here, and figure out, okay, where in the circuit is the problem. A pretty easy method of digital to analog conversion. Again, it's that current summing junction where the weighted input contributes a more or less proportion to the actual final output voltage. Okay, this concludes the binary weighted input method. We're going to go ahead and go on to our next method of digital to analog conversion.